Welcome to the first example on working with mirrors. This lesson and the next lesson, you have 3 days to do them. They're very similar type lessons. A lot of the properties that you work with in mirrors will carry over to the next lesson on lenses. There's a lot of things that you really have to try to sort out for yourself in terms of the drawing the diagram and in terms of using the formulas correctly. So get lots of practice, do everything in there, and it should help you to try to memorize as much about this as possible. So our first example, we have a 5 centimeter tall object placed 22 centimeters in front of a concave mirror that has a focal length of 6 centimeters. Determine the characteristics and dimension of the image using the scale diagram. So we're going to draw some ray diagrams and then using the curved mirror formula. You'll notice that we'll get an answer graphically that'll be very similar or close to what we get algebraically, but as soon as you draw rays, you're going to be making approximations, but you should get the characteristics down pat easily from the ray diagram. The algebra will be our more accurate calculations. So the first thing you do in step 1 is to first of all draw the object. It is 5 centimeters tall, so you can see it going up 5 spaces. 22 centimeters in front of a concave mirror, so I drew my concave mirror. 22 increments to the object. You can count them out. Has a focal length of 6, and we also know that the center of curvature is twice the focal length. So the focal length should be 6 units. 1, 2, 3, 4, 5, 6. Center of curvature should be another 6 units or 12 units from the mirror. 1, 2, 3, 4, 5, 6. And if you count out the rest of the object, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Start with this in every mirror or lens formula. Put the basics down so that you could start to draw some accurate ray diagrams. The first ray diagram I always draw is the one that's parallel to the tip of the object. To me, that's the easiest one to remember. And then note, once it hits the mirror, it reflects through the focus. So there's my first diagram. The second ray I always draw is the one through the focus. Once that one goes through, that reflects parallel. And all you really need is 2 rays to determine where your image will be, because where they cross is where the image is. And you can see that coming in now. And from there, we should be able to write some characteristics. But there is one more ray that you could draw for checking. Any ray through the center of curvature will reflect back on itself. And you can see that even the third ray crosses at approximately that same point as well. So that's a very good indication that we've got a proper ray diagram. I always start with the ray parallel to the tip of the object. Then I draw the one through the focus. After that, then I can draw the third one, but I usually only draw 2. If I was to list the characteristics of this, it's inverted, meaning it's upside down. It's smaller than the original, so diminished, and it is real because it's not behind the mirror, it's in front of the mirror, so the image is real in this case. So the scale diagram gives us a really good accurate measurement of the image, and what we're going to do is now list those characteristics graphically. If we count out how far it is, it's 1, 2, 3, 4, 5, 6, 7, 8 units from the mirror. It is 2 units below the principal axis. So if we were to fill out the chart, the image distance is 8.0 centimeters. And the height of the image is negative 2.0 centimeters. and the magnification, we'll calculate that right away. We've already filled out the characteristics. It's inverted, smaller, and real. And now we're going to do this algebraically just to check our numbers. Let's list what we know. We know the height of the object. It is 5 centimeters. We know the distance of the object. It is 22 centimeters. We know the focal length, 6 centimeters. What we want to do is we want to figure out the height of the image. We want to figure out the distance of the image, and we need to figure out the magnification. Well, let's start with the first formula. 1 over f equals 1 over di plus 1 over do. We're going to manipulate this for di. So 1 over di equals 1 over f minus 1 over do. Put our numbers in. I'll solve for this after. It's a little hard to manipulate this formula, so I usually put the numbers in, then just reciprocal it after. 1 over f is 6 centimeters minus 1 over do, which was 22 centimeters. So punch that in on your calculator. So it's 1 divided by 6, subtract 1 divided by 22, get the answer, then reciprocal it. So use your x to the negative 1 key, and you should get 8.25 centimeters algebraically. I always find it easier just to substitute the numbers and then reciprocal it after you do the calculation. The algebra involved for manipulating that is actually quite difficult, so I tend to do my substitution and just let the calculator do the work. So put that number in to 2 sig digs would be 8.3. So slightly different than our graphical result. Now that we've got di, do, we could go find hi. So hi over ho equals di over do. It's the other formula on our sheet. We're going to solve this for hi. So hi equals negative di ho over do. Put our numbers in. Negative di was 8.25 centimeters. Height of the object was 5 centimeters. Distance to the object, 22 centimeters. Punch that in on your calculator, and you get 8.25 times 5 divided by 22, and you get negative 1.875, which should make sense because we know that the object was inverted. So we should get a negative height for the image, and it's again fairly close to 2 sig digs, negative 1.9. Now to calculate the magnification, which I'll do at the bottom, well, the magnification is, I tend to use hi over ho. And if I was to do this graphically first, then it's going to be negative 2.0 over 5.0. That's the graphical answer we'll get. So 2 divided by 5 gives us a magnification of 0.40 times, which does make sense. It's less than 1, meaning our image is smaller. So there's our graphical result. And if we were to do it again using our algebra, notice I don't put the sign in for the magnification. We're going to go 1.875 divided by 5 gives us an algebraic number of, again, 0.38. So something very close to what we determined graphically. So you can see algebraically will be a little bit more accurate. There is some error when you do ray diagrams, but they do give us a very good approximation. Make sure you keep your numbers organized, the height of the object, the distance of the object, the height of the image, the distance of the image. Make sure you be very careful of the signs for virtual and real images. I've got a little chart in the notes to help you with that. There's a lot of things to really keep organized so that your numbers end up working out for you. Here's the first one with a concave mirror.